In this video, we will be discussing the performance control loop. We will first overview all the functionality of the performance controller. We'll talk about how to configure it to a specific example, and we will review the operational screens and what service menu options are available for the controller. The performance control is a PID controller, and it's used to control a process related to the compressor operation. Typically, the performance output is used to modulate a suction or discharge throttle valve. It can be used to position the IGVs or provide a speed control set point to the prime mover control. Each of these handles is typically a way to vary the amount of flow through the compressor in order to control a process variable that is affected by that change in flow. So this can be the compressor suction pressure, the compressor discharge pressure. You can control flow directly using the flow signal, or this could be less commonly something like a KO drum level that we may change with the flow through the compressor. The functional diagram is given here. This will show all of the different routines and PIDs that can affect the final performance demand. There are three PIDs within the performance controller. We have the performance controller itself, which is controlling the main process variable. We have an optional limiter 1 PID and an optional limiter 2 PID. So these are low signal selected with the main performance controller in order to limit the final demand. So this could be used with something like the motor current of the motor driver, so that the motor current process variable does not exceed a pre-configured set point, and so the final demand here doesn't overpower the motor. Now these are optional, and they can also be enabled and disabled during runtime. There is a sequence positioning ramp, so this will ramp the demand to configured values during startup and shutdown. So typically there will be a position for the reset and a position for start. So prior to actually starting the compressor, the performance demand, if it's on a throttle valve, say, could open to, say, 10% and allow the compressor and vessels to charge with the process gas prior to starting. A manual positioning ramp allows a user to set the final demand at a desired level. This can be used for troubleshooting or when bringing different controllers into and out of control. But tracking logic allows the mode, so whether you're running in auto mode or PID control versus manual mode, where the manual demand ramp has control, tracking allows you to switch bumplessly between these two controllers. Now, a part of load sharing, or a part of performance, is the load sharing logic, but really we treat this as a separate control module. However, the demand from the load share PID is sent to the performance LSS, and when load sharing is enabled, it is switched onto this LSS and the performance controller is switched off. But this allows the two limiters to remain enabled on the load share PID so that you still have those protections active while in load sharing. Decoupling logic is used to anticipate the effect of other controllers on the performance control. So if the anti-surge stage 1 valve position opens, this will recycle flow, and say if the process variable is your suction pressure on the compressor, we know that that variable is going to go up due to that increase in flow from the discharge side, and now our performance controller is going to respond. So we're going to go ahead and try to pre-position the performance controller based on this valve position. So those are the control functions within the performance controller. When we're configuring this, we'll be setting up things like the set point range, the process variable that we're looking to use on the controller, whether we want to use the limiter PIDs, what their set point ranges are, and then the sequencing position, setting the rates and the valve positions that we ramp to during startup and shutdown. So let's go ahead and take a look at some examples that the performance controller can be applied to. So here's an example of a PNID that we're going to go ahead and configure the performance controller for. In this example, we've got a suction throttle valve, and the controller has got a process variable of compressor suction pressure. So we are going to use the performance controller to modulate this valve in order to control the compressor suction pressure to a desired level. Now here we also have a common suction header that is shared between multiple trains, and later we're going to use the same example to configure our low chair controller. But for this example, the purpose is just to configure up the performance side of things, so we're going to start there. Here we have a motor driving our compressor section. So the motor current signal is coming back on an analog input. We're going to set that up on a limiter PID so that we can protect the motor from being overpowered by our suction throttle demand. The rest of this application would be the anti-surge control. We're not going to get into that in this video. That will be covered in a different example in a different video, but all the control related to the anti-surge controller will be covered in detail in a separate video. But for now, we'll just know that the unit has been configured for this anti-surge control, and that this operation is the performance and the anti-surge controller do influence each other, but they operate independently, and we have some strategies for what we call decoupling the influence of our performance control and anti-surge control, but we're going to cover those in detail in a different video. So for the purposes of this example, we're setting up the performance controller, and the anti-surge control is going to operate independently. So we'll run through the configuration menus on how to set that up. Once you're in configuration mode, you can go to the performance control menu. And here we need to select what our process variable is. So the drop-down menu has a list of 5 available functions. We can use a pressure signal from one of the 2 anti-surge control sections if they're configured. Or we can use a dedicated input. And this can be any 4 to 20 milliamp signal that's affected by the performance demand. But for this application, we're going to use the anti-surge section 1 suction pressure signal. So we'll go ahead and select that. And once selected, then the additional configuration items get listed below it. Here we need to set up the minimum and maximum set points. So these will be based on what is the typical operating range for this particular application, and this will define what the performance set point is limited to. So if we put this at, say, 300 to 600, we can't tune the set point outside of that range. So this could help prevent the unit from going to an undesired operating condition. Now, if you need to invert the signal, this will change the action of the control. So if it's yes, if we check this box, the control will be reverse acting, meaning that a decrease in the performance demand should result in an increase in our process variable. In our PNID, we had the pressure signal that we are controlling downstream of the actual suction throttle valve. So that means that an increase in the suction throttle valve will increase the flow to that sensor, increasing the pressure at that sensor. So we have, in this application, a direct acting control. The set point rate will define how fast the set point ramps from the current position to, if you're using a go-to value or a raise lower command, that's the rate that it'll move at. Set point tracking, we're not going to use that in this application because we know that the pressure we want to control the suction line at never changes. So we'll set that up with the known value we want to control to at first. However, if you do check set point tracking, then during your startup sequencing, the set point just follows the process variable, so that once you go into PID control, that is the set point that the unit uses. So it allows for a smoother transition into PID control, but then your operator's got to go in and set the pressure set point to the desired level. So on our next page, we can select whether or not we want to use a remote set point. This would be a 4 to 20 milliamp signal that tells the unit what the set point is, say from a DCS. In this application, we're not going to use that, so we'll leave that no. There's an option for driver limit tracking. This would be used if the performance output was driving a speed set point to the prime mover control. If we check this box, then we can have a Boolean input tell the Vertex that the prime mover controller has been limited externally, so that the Vertex knows it's no longer controlling that set point, and it'll go into a tracking mode. Use remote manual demand. We're not going to use that in this application, but it is available as an option that an analog input can be used to remotely set the valve position directly or the final performance demand. So this will actually take over that manual positioning ramp using a 4 to 20 milliamp signal. The performance drive type is mainly used for display, so if I select the suction throttle valve on the graphics and the runtime screen, we can put in a suction throttle valve there, or discharge side, or if it's to the prime mover, then we show that in the graphics as well. Now, IGV, if that is selected, it also drives some graphics, but it also enables online detection in the anti-surge control. On the next page, we get into the performance sequencing configuration. So we can first set the reset position, and this will be the position the final demand ramps to once all your trips are cleared. The purpose of this would be to pressurize the vessels and the compressor prior to starting with the process gas. The startup position is ramped to after a train start command has been received. So by increasing the demand, we allow for the adequate amount of flow through the compressor during the startup sequencing. A startup delay can be added to delay how long it takes between receiving the start command and actually ramping to the start position. The sequence ramp rate defines how fast we're going to ramp between these various positions, and we can select whether or not we want to use a remote start. So remote start would mean that we're not going to receive a Boolean input from the prime mover control to indicate that the unit is started. If this box is checked, then once all the trips are cleared in the Vertex, we simply ramp to the startup position. The use manual start, this option allows you to go through the start sequencing of ramping to the reset position, then ramping to the start position, and once the startup completed signal is received, instead of going automatically into PID control, you can remain in manual control to keep the valve at the last position. This may be used to allow operators to stabilize the process. Then once they're ready, go ahead and enable the performance PID controller. And that's it for the performance configuration. Next we can get into the limiter control. So back on the configuration menu, once performance has been selected to be used, the limiter control and the load sharing menus become available. So we can go in and go ahead and configure our limiter. We know we're going to want to set up a limiter on the motor current, so we will select that from the drop-down list. Now selecting this means we need to have an associated AI configured, and we'll cover that in the next slide. But then we can go ahead and set our minimum and maximum set points. This is similar to the performance controller. This defines what the set points can be tuned to while the unit is in operation. We'll need to provide an initial set point, so this will be somewhere less than the overpower trip point of the motor, and we'll go ahead and limit the performance output once the motor current gets up to this level. So we know this isn't going to change. We're going to set it in as our initial set point, and once the current comes up, that's just what we control to. Now, depending on the application, you can invert this. So if increasing the performance demand output results in a decrease of the selected performance variable, then you're going to need to invert so that this is reverse acting control. We can set the set point rate, and then the limiter 1 is available to be configured with a remote analog input. So the DCS can actually set what the set point is once the unit is up and running via that analog input. So how do we achieve the I/O for that configuration? The suction pressure of section 1 is going to be used for performance, and we're already using that for our anti-surge control. So no further configuration is needed as far as the analog input on that. But we do have to add in a motor current 4 to 20 signal to be used by our limiter. We also need to configure some Boolean inputs to indicate the train startup sequencing. So here we're going to get the train start command and the driver startup complete command. And these will be used by the performance sequencer. And once we get this startup complete command, we go ahead and go into PID control. We also need to configure an analog output to drive the throttle valve. So when you configure the particular channel that you want to put the performance output on, the scaling is automatically fixed to 0 to 100. So this would be your minimum position and maximum position on the throttle valve. If, say, performance was configured to be the speed set point for the prime mover control, the scaling is still set up for 0 to 100 here, and that relates to, say, 4 and 20 milliamps, and that needs to be configured then and scaled on the prime mover controller to represent, say, the minimum and maximum governor. Once you selected this analog output to be used as a driver for performance, you can use a fault shutdown, meaning that if the Vertex detects a circuitry failure of the analog output, that you can shut down the unit. Or if this is unchecked, then the failure will show up as an alarm. And there is a fallback strategy here that will show in the service menus. Fail open actuator for performance could be used, say, on an IGV positioner where it takes 20 milliamps to actually close or go to the minimum position of the actuator, and that way if the output fails or if something on that driver fails, that the actuator actually goes to the full open, and that would be the safe failure mode. So this is really setting up what is the safe position, and if this box is checked, what we do in the Vertex is go ahead and send 4 milliamps when we're demanding 100% and send 20 milliamps when we're demanding 0%. So this does have an effect on the actual milliamps going out, and this should be checked appropriately. For most applications, though, this will be unchecked on the performance control side, but nearly almost always checked when you're using this as the anti-surge command output. And that's it for the performance configuration. I think it's really a straightforward setup. If you're familiar with our 505, I think those menus would look familiar to you for the aux or cascade loops. We really follow a consistent setup there on those controllers. So now what we're going to go ahead and do is move into the runtime pages for performance, and we'll give an overview of the pages that are available for not only the performance PID but also the related functionality in the performance controller. So to start, we're going to look at the performance control page. This page has all the information that is needed to operate the performance controller. It displays the process variable here in the gauge. This range will be set up with the analog input, so you'll have an idea of where you are within that scaling. The units are pulled in from the analog input that's used as the performance variable. The set point is displayed below. Now when you're ready to adjust these and you're up and online and in control, the adjustment arrows will be displayed here. And the current PID output is displayed beneath there. So over here we have status messaging up at the top. This will display what is currently controlling the performance. So if you have a remote set point, it will say enabled with remote set point. If it's in manual, this would indicate that the controller is in manual. Beneath that we have the final performance demand. So if the PID value is different than the final demand, then you're going to be operating on some sort of a limiter, but that will be indicated in the messaging, and then you'll see in the later screens. We can see why exactly is the PID not in control of the output at this time. So this is a very useful page. You can transition between your control mode of auto and manual. And if the controller cannot be enabled, the current inhibit conditions would be displayed here. The menu bar allows different commands to be given to the performance control. So if you hit commands, you'll be given an option for direct set point entry, or if you're in manual mode, you'll have a direct valve demand entry. You can enable and disable the remote set point from the DCS, that would be the analog input. And you can also get to the dynamics page to do your PID tuning. The sequencing control page, this is also accessed off of the main menu. This screen is very useful when going through your startup. So it will display the current state of the sequence ramp and what is the state of the prime mover. Really, this relates to the prime mover sequencing. So if it's ready to start state, that means all of your trips are cleared, and then once that condition is met, we're going to go ahead and move to the reset position. Once we receive a start command, then we'll ramp to the startup position. The LEDs will tell you where you're at in that process. If you want to halt the manual demand for some reason, you can do that here, and then pressing continue will allow it to continue on up to either the reset position or the startup position, depending on where it's moving to in the sequence. A direct position can be entered using the soft key here, and then you can type in a value that you want to go ahead and set the sequence ramp at. So this can also be used after startup to be a manual limiter on the performance PID output. So if the performance PID, say, were unstable and you wanted to freeze the output to provide a troubleshooting strategy, you could bring this limiter back down, the sequence ramp back down, and use it as a limiter on the performance demand. So it's really a useful tool even after the startup is completed. On the performance demand page, this can be accessed from the home screen, the demands, and then using the performance soft key. We'll bring you here. This shows you what has control of the current valve demand output for the performance. So in this case, the PID is the lowest signal on this LSS bus, and thus that is driving the final demand. The green arrow will tell you what is driving this demand here. And then if you go into manual, there's some graphics that will display this switch has changed state as well. So here now we've got the limiter 1 control page. This is the control page for the limiter PID on the performance LSS. So a very similar structure to the performance controller. We have our process variable shown within the gauge, a set point down beneath it. This value can be adjusted with the adjust component here. It displays the current ramp rate and what is the current PID value. We have status messaging up in the upper right hand corner. and what is the current demand for performance. So this would show you what the final performance demand is, and it gives you some information on when this PID would transfer into control of the actual performance demand output. Okay, so now we'll go ahead and do a little demo of our performance controller. We will use the operational screens to operate the unit. To start here, we see we are in a shutdown state, and I am on the performance sequencing control page. So I got here by going home and down to the sequencing, or I could just press the 4 hotkey. So we are tripped, and the valve demand is currently being held as 0. So I'm going to go ahead and issue a reset, which should bring us to an untripped state, and we are going to start moving towards the reset position. So here you can see what your reset position is. It's going to go up to 10%, and now it's going to hold. And at this time, we are waiting for the train start to command from the prime mover. So now we're holding at the reset position and waiting for the prime mover to be started out in the field. We'll go ahead and let the operators do that now. And here we've received the start command, and we're ramping up to the startup position. Once we get there, we're going to hold that position until the startup completed signal has been received. And there we received the startup complete. So we have gone into manual demand. Now this is a configuration option. In this example, we've chose to use a manual start. So once the startup is completed, we just hold that last value and allow the rest of the system to go ahead and stabilize. So here you can see our anti-surge control is under sequence control, and it's ramping down towards 0 to load the compressor. So our performance PV is fairly unstable at this time while the anti-surge valve is coming down. We should start seeing this pressure fall off as that valve is closed and the recycle flow is less. Alright, and now our anti-surge valve is closed and our process still has some movement. So we'll go ahead and let that stabilize a little bit. Okay, so we have a set point of 200 psi. We're going to go ahead and enable our performance PID controller, and we should see that this valve begins to increase to pull up our process variable to be controlled at the set point. So here the valve is opening up, and the performance PV is coming up as well. A little bit of overshoot, and now the valve is reducing to pull that into our set point. Now we're in closed loop control on our compressor suction pressure using the performance demand output on a suction throttle valve. So here from the runtime screens, I can access the control pop-up. This is a useful tool to be able to interface with the controllers from pretty much any screen that's in the GUI. And here I can increase the set point, so if I need to come up a little in pressure, I can do that from here. I can also go back into manual control, and that will hold at the last position. You can see that transition was bumpless. And now I'll go ahead and increase the valve demand and go back now into auto, which will control it back down to the set point that you had in there. The limiter also has a pop-up, and similarly this page can be used to interface with that controller, so as the motor current comes up to that value, it will take over the valve demand here to reduce the output and prevent the motor current from going any higher. We can show that here on our performance page. If I go into my limiter control and bring the set point down to 1400, so I'll go ahead and enter that directly. Now we're going to see that that motor current will come down to the set point of 1400 once it ramps there. Now the valve demand hasn't moved, it's still under performance control. Once our PID for this limiter gets less than the current output position, it'll go ahead and take it over, and these should match. Now our limiter PID is pulling down the valve demand output, which has an influence on the motor current, and in that way we've taken over the performance demand in order to maintain the motor current. Now on the performance side, it is no longer in control, so we have a status messaging enabled, not in control, and increasing the set point here does not have an effect on the valve. Okay, so now we've gone through a demo of the performance controller and seen how the runtime pages can be used to assist with the startup and operation of the performance controller. Let's look at the service menus that are available for the performance controller. These provide tunable values that can be changed while the unit is online to tweak and dial in the performance operation. So in the service menu, once performance has been configured, it becomes available as an option here, and as well the sequencing menu becomes an option in the service menu. On the first page, we can adjust our rates. So these tell us how fast the set point will move when adjusted. And then we have our performance variable, or the demand output failure mode. And this will define what action to take if the driver fails or if the performance process variable analog input fails. This can be set to fail to manual, in which case the performance demand output will hold at its last position, or it can be set to fail to max or fail to min, based on what may be the safer operation given that we've lost control. You can enable or disable manual demand, so if this is unchecked, then the operator cannot put the performance controller into manual mode. And here you can enable and disable the set point tracking feature, which we covered in configuration. Hold service changes. If this is yes, the rates defined up here at the top will persist through a power cycle. If it's unchecked, then these rates will get reset based on the configuration value of the set point rate. So on the second page, we can set the minimum demand limit and the maximum demand limit. These set the clamps on the final demand, minimum and maximum position. For this application, since we're driving a suction throttle valve, we want to set the minimum demand limit up enough that the performance controller cannot reduce the valve position such that it starves the compressor of all flow, leading to a surge condition. If we go into the sequencing service page, here we can adjust the reset position, the startup delay, and the ramp rate. So when you're commissioning a unit, you can come into the service settings here and adjust these values based on what's being observed in the field. Within the limiter PID service page, You can set your rates for the set point and also the PID threshold value. Now the manual contains a very detailed description of what this threshold is doing, but essentially this will define how and when the PID comes in and out of control on the LSS bus. The LED here indicates that the control is enabled, so that means that it can take control of the output on the LSS, but the limiter can be disabled if needed from the service page. And this concludes our overview of the performance controller. The intent has been to show what functionality is included in the performance control, some example applications of the performance control, and then we went through how to configure the unit, how to operate the unit with a little demo, and finally wrapping up with the service parameters.